So today we are going to discuss in this session about the second order process, and which is simply a continuation of what we have started in the previous session, that is a first order process. So by analogy we can understand that a second order process is something where the input and output, they are related by a second order differential equation. So if I have this system schematic, that inflow is f prime t, the inflow deviation variable is, input deviation variable is f prime t and output deviation variable is y prime t, then we have this as a second order system equation, where this side we have a second order derivative operator and we are thinking strictly about the lumped parameter system, right. That is the ordinary differential equation will be the outcome of mathematical modeling, and let us say it is or it may be, in any chance it may be a nonlinear equation which we have linearized and we have got the second order differential equation. So you see that we will reduce the number of constant coefficients upon dividing the entire equation by a naught, and we call this a2 by a naught. This has got a physical significance, we will discuss about that. Let us say it is tau square and this is 2 tau zeta and this is the as usual Kp. And I have mentioned during the discussion of the first order process that this Kp, which is the static gain or steady state gain, that is universal to any system, right. It is not only restricted to first order system, whereas the time constant is specifically a term or parameter associated to first order system. But here similarly we have a new term tau, not tau p, right. So tau is a natural, is referred as natural period of oscillation. Zeta is a damping factor and Kp as usual is a gain. We will discuss about the physical significance, that why these are called or referred as the natural period of oscillation. But before that, let us go for the Laplace transform and get the transfer function of the second order system. So here the initial conditions are definitely the y prime 0 is 0 and also the first derivative at 0 will be 0, right. So with that consideration, if I take the Laplace, it will be tau square s square plus 2 tau zeta s plus 1 whole bracket y prime bar s is equal to Kp into f prime bar s. So y prime bar s divided by f prime bar s, that is the transfer function, it is Kp divided by tau square s square plus 2 tau zeta s plus 1. So that is the transfer function of a second order system. Now before going into the understanding of dynamic response of a second order system, let us try to understand the physical significance of the different parameters what we have introduced newly in this second order response. See, here in second order system they are susceptible to oscillation, they give oscillatory response. So that is why what the physical system, the very baseline physical system what we consider here is a pendulum. right. So let's start from discussing the pendulum, the very basic physics of this simple harmonic motion, and then we will go for periodic motion as well. So let's say this is the point of suspension, the string length is L, the mass of this bob is M. So here we have mg, here we have the tension acting, right, and this is theta. So in this direction we have, this will be definitely theta, and the restoring component will be mg sine theta. So as it's a kind of this rotational kind of motion, right, so we can apply the torque balance if there is no other resistance, and let's say it is a simple harmonic motion, or rather not a simple harmonic motion, let's consider it's a motion of a pendulum, and it's without any resistance of air or without any forcing function from outside. Simply initially we have given a displacement, and with that displacement the pendulum continues to oscillate, right, as there is no resistance of this fluid. We have created a vacuum. So under this situation, the torque balance, we know that I into alpha is equal to this summation of torque, right. So what will happen here, the torque produced by the component of this mg is mg sine theta into L. This angle is 90 degree. So force multiplied by the distance is will be giving you the torque, and that is a kind of restoring torque, right. So it intends to reduce the value of theta. So write that I into d square theta dt square is equal to minus of mg sine theta into L. Now again, for this point mass, the I is ml square into d square theta dt square plus mg sine theta into L equal to 0. So d square theta dt square plus this g by L into sine theta equal to 0. Now for theta, now we introduce this simplifying assumptions of small displacement, theta less than 4 degree. So sine theta can be approximated as theta. There is an alternatively we may refer this step as a linearization, but linearization here we are not following the typical Taylor series expansion. Basically Taylor series expansion of the sine theta will give you the same term theta s, right. So the thing is, we are simply linearizing it based on this consideration that theta is very small from the steady state value, which is 0 degree. So with that, and we refer this g by L is omega n square. So d square theta dt square plus omega n square theta equal to 0. So that's the typical equation of simple harmonic motion. Now if I have resistance, right, if I have, it's now think that it's a kind of damped oscillation and we have a fluid resistance. So next again we will write this torque balance. So I into d square theta dt square is equal to minus of mg sine theta into Fd, the drag force, into L. Now the drag force, if we consider Stokes law, is equal to C into d theta dt. So if we go for writing this I is equal to ml square and simplifying assumption that sine theta is equal to theta, then we will get that Fd divided by m into L into d theta dt, not Fd, rather it is C, the C into d theta dt, right, and this Fd is C into d theta dt. So, C divided by ml square, and there is also a L here. So, that cancels out, giving ml plus theta into omega n square is equal to 0. So, let us keep this as it is. Okay. Let us keep this as it is. Now, in additionally, if I have a force which is a periodic force maybe, right, because in the under this condition what will happen to theta? See, if I give a positive displacement like a large value of theta, if I am displacing this bob here and release it, so it will execute a damped oscillation. Finally, the oscillation will die down. Now, in order to sustain that oscillation, what we have to do? We have to give a forcing function. And for this oscillation to sustain, we definitely have to give this typically a constant force, a periodic force. But if I want that, okay, I am releasing from here and I want that pendulum to stay here, the bob to stay here, then the force will be a constant force, but after some oscillation it will be attaining the static equilibrium somewhere here. So, the situation what we perceive may be like this, right, okay, or it may start here this theta 0 is not equal to 0, or it may start from somewhere here where theta is equal to theta 0 is 0, we are giving a force and it attains a final equilibrium. So, under this situation what will happen? We have to include the moment produced by this force, external force, right, that is F. That force is an external force and it is acting constantly on this mass of the dead weight of this pendulum, and the pendulum dead weight attains some fixed position, fixed theta value not equal to 0 after some initial oscillation. So, under this situation the equation of motion will become d square theta dt square plus C divided by ml into d theta dt plus omega n square into theta, and here on this side for the moment balance it will be F into L, right. F we are giving in alignment with this direction of motion. So, it is, or it may be a component of that force which is aligned along the direction of motion. So, that will be equal to F into L by ml square, right. Now, the entire equation if I divide by omega n square, so we will get omega n square here d square theta dt square plus C by ml into omega n square into d theta dt plus theta is equal to F by ml into omega n square. Now, omega n square, you see, it is the natural frequency of oscillation, and inverse of that we define tau as 1 divided by omega n, and essentially it becomes tau square d square theta dt square plus. Now, see, what about the damping? The damping actually, whenever we have an external force field, it may happen that this value, see here we are saying that it will oscillate and attain this final. It may happen that we are giving a force and it attains the value somewhere like this. Okay, it can also attain the same value, the theta, upon oscillation, and it may be attaining this with a much sluggish pace. So the three processes are distinct, right? And that depends on the value of C. So what we do, this entire group we write as 2 tau zeta, right? Such that if zeta, see the damping factor, why it is being referred as damping factor? Because we are considering a standardized value of 1, and if zeta greater than 1, right, sluggish response. So this we call as overdamped, right? And the physical reality is that pendulum is suspended in a lube oil which has got a very high viscosity and the value of C is high. So the respective, if I equate this entire group to 2 tau zeta, then zeta becomes greater than 1. So that is a sluggish response and we refer it as overdamped response. And zeta equal to 1 at the verge of oscillation, it's called critically damped. However, for zeta less than 1, so here if it is zeta less than 1, it will give you underdamped response or oscillatory response. This is zeta greater than 1 and this is zeta equal to 1. So zeta less than 1 is oscillatory response and we call it underdamped. So plus this theta is equal to some constant which is the static gain into F and Ft. Ft is the external forcing function and in a sense it is input. So you see that whenever we are generalizing this equation of pendulum, we are getting the typical second order behavior. So the pendulum is a baseline system to understand the second order system, right? Now, in real life, why we are studying this? We are studying this because we have seen different instruments like a pressure gauge maybe, right? A pressure gauge where the spring is extremely sensitive, what will happen? And the bellow and not the bellow, the C-type pressure gauge, right? This arc is extremely sensitive to external pressure. So what will happen? If I say initially it is 0 and finally it is say 2, this needle will displace and will indicate these 2 atmosphere. Now if the response is something like that, if initially it's 0, we have applied the pressure and it slowly goes to this 2 atmosphere. Therefore, the system is basically critically damped. Initially there is no change and after that it slightly goes on changing and attains these 2 atmosphere, right. So that is the overdamped response. If I apply now pressure, now if the spring, here in this case the spring is rigid and tight, right, and it needs a higher amount and it gives a lot of resistance to that specific displacement. But if it is at the verge of oscillation, what will happen? So if I am giving the pressure, it will move like this and attain this 2 atmosphere. And on the other hand, if we further increase the sensitivity of the spring, the situation will be something like this. It will oscillate about 2 atmosphere and finally settles to 2 atmosphere, alright. So it will oscillate before settling to 2 atmosphere, just like this. So just like the pendulum, right. So pendulum initially is at neutral position, now I am giving a force. So it may attain a definite specific location, right, based on the and it will be dictated by what sort of fluid it is suspended in. If it is a lube oil, it will give you a high resistance. So with the same force, it will very slowly and sluggishly attain this equilibrium value of theta. If it is less resistant, like water maybe, initially it is lube oil and the respective response is overdamped response, right. So if it is water now, so it has got less viscous resistance, because you see this is simply an outcome of the Stokes law, and in Stokes law we know that Fd is equal to 3 pi mu dp into this V, right. So, this constant term mu dp everything we lump into C, and V we change as L into d theta dt, and so C is equal to 3 pi mu dp into L. So, the situation is just like it's simply a reduction or reductionist form of Stokes law, right, a simplified form of Stokes law. So, what happens if I have now water? See, if it is filled or suspended in water, and pendulum is initially here, we have given force. So, it's at a fast pace it will attain this final position just like this. So, it is critically damped, right. So, it is a specific situation where this damping factor, empirically introduced parameter, that is a damping factor, attains a value of 1. But if it is here and we are giving a force, so what will happen? It will oscillate and finally settle down to this specific equilibrium position. Okay? So, the response is something like this. So, pendulum is a baseline physical system to study and understand the second order system. Okay? So, in general now, for any device, we will no longer keep the theta, but we will consider it as a general output, and that sort of behavior maybe, or we will see it can be exhibited by different possible systems like a U-tube manometer, like a control valve, like an LCR circuit, okay, like a typical thermometer itself, where previously see in mercury in glass thermometer can be perceived as a second order system and also as a first order system. When it will be perceived or considered as a first order system? Where we neglect the capacitance of glass and thermal resistance of mercury, right. So, but if we consider them, if we now consider them, then mercury has got both the resistance and capacitance, glass has got also the resistance and capacitance. So, these two are individually first order systems and which are connected in series. So, we will see later in our discussion regarding the origin of the second order system that if we connect two first order systems in series, it becomes second order system, right. So, the same mercury in glass thermometer based on the relative values of these resistance and capacitance of glass and mercury respectively can behave also as a second order system. So, in general we will be replacing this theta and we will write the general differential equation for the second order system as this. What we have originally written, right. Now, it must be clear to all of you that why we are referring this tau as a natural this period of oscillation, zeta, why it is a damping factor, right. This term 2 has been introduced in order to normalize this entire group of term such that into 2 tau zeta, right. Now, zeta has been normalized, right, that is the logic we introduced to, such that zeta, its mean value or somehow a threshold value is equal to 1. If it is greater than 1, it will give some sort of specific response which is a overdamped response. If it is less than 1, it will be giving an oscillatory response, that is an underdamped response. So, that is the logic behind studying pendulum in relation to the second order system. So, next we will try to discuss the dynamic response of a second order system towards any step input, right. And we have to consider the 3 different types of response separately, because we will see that in the transfer function, you see, once we have the transfer function of the second order system, what we have to do? We have to multiply it by the Laplace transform of the step input, and we have to go for partial fraction because it is quadratic expression of S. So we have to break it down into two linear factor and have to follow the typical methodology of partial fraction. So whenever we are going for partial fraction, we have to be very careful or cautious about the nature of the roots. Now it may happen the two roots are real and distinct. We may have two roots as complex conjugate or real and identical. Let's see what happens here. So dynamic response of second order systems. What we are talking about, that y prime bar s is equal to Kp divided by tau square s square plus 2 tau zeta s plus 1 into f prime bar s. Now here we are replacing the expression for step input, right, for which f prime bar s is equal to a by s, where a is the step height. Now you see that this will be Kp by, we can write it as s minus p1 into s minus p2 into s. Numerator is Kp into a. Now what will be p1 and p2? The roots of this equation tau square s square plus 2 tau zeta s plus 1 is equal to 0. So you see this tau square s square plus 2 tau zeta s plus 1 is equal to 0. So s will be minus 2 tau zeta plus minus 4 tau square zeta square minus 4 tau square divided by 2 tau square. So it simplifies to tau by zeta plus minus under root of zeta square minus 1 by tau. Right? So P1 and P2, if see zeta greater than 1, P1 and P2 are real and distinct. So this denominator of any transfer function when factorized, you see the respective roots are called poles, right? So P1 and P2 are poles of the transfer function. So they are called poles of the transfer function. Now for zeta greater than 1, these poles are real and distinct, right? That is the case 1. Now case 2, if zeta equal to 1, P1 and P2 both are equal to minus zeta by tau. And 3, if zeta is less than 1, then P1 and P2 will be minus of zeta by tau plus minus I into 1 minus zeta square by tau, right. So P1 and P2 here real and identical, and here they will be complex conjugate. So this is overdamped according to our definition. This is critically damped. And this is underdamped. Right. So for these three different values of this P1 and P2, we will have three different responses. In general, you see, we can write this y prime bar s as C1 divided by S plus C2 divided by S minus P1, C3 divided by S minus P2. So y prime bar t will be equal to C1 plus C2 into e to the power P1t plus C3 into e to the power P2t. See, if these are real and distinct, we will get, see, for this term, group of term, hyperbolic function, because this P1 and P2 are real and distinct, for zeta greater than 1. They are, if P1 and P2 are same, right, if P1 and P2 are same, then definitely we will have here the C2 divided by S minus P1 plus C2 divided by S minus P1 square, right. So there we will have the response as y prime t equal to C1 plus C2 plus C3t into e to the power P1t, something like this, some exponential function coupled with a linear factor of t. And if zeta is less than 1, it will be something, some y prime t will be equal to some trigonometric function, right, according to Euler's theorem. That is, e to the power I theta is equal to this cos theta plus I sin theta. So if it is theta less than 1, because we have got the e to the power I term, right, and if we split that, we will get this trigonometric function. So what are the actual form of the function? I am not solving it, it is given in all book, it follows actually some tedious algebra. So that is why I am not doing it, right. So, and you do not have to remember all the expressions, you do not have to remember this overdamped expression, right. It is functionally quite complex, but for underdamped and critically damped, you have to remember that what will be the expression of y. So now we know the nature, basically we know the nature, but exact function requires this algebraic solution, and the algebra is a bit tedious. So if zeta is greater than 1, right, y prime t is equal to a kp into this 1 minus e to the power minus zeta t by tau cos hyperbolic zeta square minus 1 t by tau plus zeta divided by zeta square minus 1 sin hyperbolic zeta square minus 1 t by tau. Right. So let me check it once again. Yeah. So it's fine. This is the expression for overdamped response. If second case zeta is equal to 1, y prime t, as we have to note that it will be a term, some constant plus some within bracket or e to the power function of t, then within bracket c2 plus c3t. And what is that exactly? A kp 1 minus 1 plus t by tau into e to the power t by tau, right, e to the power minus of t by tau. So that is the critically damped response, and for the underdamped, that is if zeta less than 1, y prime t is equal to a kp 1 minus zeta divided by under root of 1 minus zeta square, then sin e to the power minus zeta t by tau, or probably this zeta will not be there. Yeah, there is no zeta here, into sine of omega t plus phi. Now where omega is equal to 1 minus zeta square by tau, and phi, the phase shift, is tan inverse of 1 minus zeta square by zeta. Right. So these two expressions you have to remember. Right. So what is the exact nature of the response? So, final value in all cases, see, y prime infinity is equal to AKP, which corroborates with the definition of gain. Here also it is AKP, here also it is AKP. Now, how it is being attained? Now, y prime t versus t if I plot, and this is the final value, which is AKP. Critically damped will be something like this. Critically damped, this response will be something like this. Overdamped will be like this. It's slowly and progressively growing, and as the value increases of zeta, so it will be the response, the y for a specific time will be lower and lower. And we have underdamped response, where the zeta value further decreases. So, here zeta may be 10, zeta 5, then zeta equal to 1, 0.8, zeta 0.5, right. So, this too, the oscillatory response corroborates with this expression. Critically damped, it's a singular one, it's this one, and overdamped, this 2 where zeta equal to 5 and 10, right. Now, previously in first order system, the responses were pretty similar to this or critically damped or this or this. Exactly, they are not same, because here the derivative for all these functions will be 0. At time t equal to 0, the derivative expressions will be 0, right. But we have got a specific type of response which we were unaware of in first order, that is oscillatory response. So, we have to focus specifically on this oscillatory response, right. And how to characterize this oscillatory response, that we have to understand in detail. Because oscillatory response, you see, finally it will settle down to the same value of AKP. But how fast it will settle down, and when for the first time it will be reaching that specific value. So, these are important parameters to understand, and they must be characterized by introducing analogous terms, okay? And how fast the oscillation actually decays down, what is the maximum value. So, everything comes under this category of understanding this oscillatory response. So, our topic is how to characterize the oscillatory underdamped response. So, here you see that if I draw a specific oscillatory response, a single one, this is the final value, and an oscillatory response is like this, right. So, the first quantity will be interested in what is the maximum cross with respect to that final value, right. And this is defined formally as overshoot. What is that? Let us mark the point this as A, this as B, right, or point this as B, or let us mark not the point, let us say this one is A, this one is B, right. B is the final value which is equal to AKP, A is the maximum height, okay. So, overshoot is basically A minus B by B. That is this divided by this. Okay. Or rather, if I define A from here, then we may erase this A by A minus B, we can write simply as A by B. Is defined as overshoot. How we can find that? See, we have got the expression of y prime as AKP 1 minus e to the power minus zeta t by tau divided by under root of 1 minus zeta square into sine of omega t plus phi. Right. So, this is the maxima. So, what is the condition of maxima? We will set dy prime dt equal to 0 and solve for t. Actually, it is a multiple solution Tn or Ti rather. I equal to 0 to n, right. So, I equal to 0 definitely is this value because this is the first point at which this dy prime dt is 0. So, I equal to 1 is the value which corroborates with this A, right. So, y prime t1, if I calculate this t1, right, from the solution, I am not doing the solution by myself. So, y prime t1 is basically A plus B. So, A is equal to this y prime t1 minus B. Or let us write this A1 and B1 because this is A will be getting confused because A is the step height. So, A1 B1 and A1 minus B1. So, once you have got this A1 and B1 is AKP, so we can find out the overshoot. And this, if you do that, it will be, you will be getting that overshoot is equal to minus pi of pi into zeta divided by 1 minus zeta square. Next, decay ratio. Another important term. So, what is decay ratio? See, the oscillation, its amplitude actually decays down. So, in the first peak, let us say it is A1. In the second peak, let us say the excess is C1. So, decay ratio is defined as C1 by A1. The second peak excess divided by the first peak excess. Okay. So, what we have to do? See, I equal to 1, this is I equal to 2, this is I equal to 3. So, C1 we can write as y prime of T3 minus AKP and A1 is basically already we have found y prime of T1 minus AKP. Right. So, C1 and A1 we can find out and we will substitute it back, we will get the decay ratio. And technically we will get it square of overshoot. If we exactly do this and we get 2 pi zeta divided by under root of 1 minus zeta square. In the handout this minus sign is missing, please get it rectified. So, first one is overshoot, the second one is decay ratio. The third one is the period of oscillation. Right, T. And what is that? T is equal to 2 pi by omega. So, 2 pi tau divided by under root of 1 minus zeta square. So, what is the period of oscillation? This. This is the period of oscillation. Right. So, this period of oscillation we can calculate from the expression of omega we have got, because this omega you see is 1 minus zeta square divided by tau. So, from there we can calculate this period of oscillation. Third is, sorry, this is third. The fourth one, I will not find out the exact value, it is called rise time. The time, the smallest time at which y prime attains its final value. That is called the rise time. Okay. So, by definition, This must be the rise time. So, 5 is called response time. The time at which y prime permanently enters the plus minus 5% band of the final value. Right. What is plus minus 5% band? Let's mark 1.05 which is above 5% AKP and also mark 0.95 AKP. So, this is the band. Right. So, you see that here it enters, but again it moves up. Here it enters, again it moves out. Here it enters, again it moves out. Here also the same. But after this point, here, once it enters this band, it's never moving out of that band. So, this is the response time. Okay, these are all the response time of this second order system. Now, rise time, response time, overshoot, decay ratio, we have got it, and period of oscillation, that also we have discussed. And finally, we have to understand what is called the natural period of oscillation. Already the physical meaning also we have discussed in the context of pendulum, but here we will do that from a different perspective. We will try to understand this from a different perspective. Right. See, the natural period, even in case of pendulum, we have noted it for undamped system where the zeta is technically equal to 0. Now, for a general second order system, so this is natural period of oscillation. Which is tau, right? And also we can say that this is the inverse of that is the natural frequency of oscillation, which is omega n. So, here you see that we have the general second order transfer function Gs as Kp divided by tau square s square plus 2 tau zeta s plus 1 into this f prime s. Let's set zeta equal to 0. So, this is undamped system, right. So, which corresponds to a transfer function that this is f prime bar s. Now, what you can do that, let's consider a step input Kpa s, and we can take out this tau square. So, s plus j by tau, j is under root of minus 1 and s minus j by tau, right. So, Kp into A by tau square 1, or let us say it is 1 by S, let us write that in this way, 1 by S plus the C1, or rather let's write it is C1 divided by S, C2 divided by S plus j by tau plus C3 divided by S minus j by tau, right. So, let us find out the values of the C1 and C2 by this partial fraction methodology, and this we will get as half and half with minus sign. So, basically if we find out this C1 and C2, what I will get? This Kp into A, what I will get? Kp into A, this will be 1 by S minus half S plus j by tau minus half S minus j by tau. Right. So, upon taking this Laplace inverse, this will be 1, this will be minus half into e to the power minus j by tau minus half into e to the power plus j by tau, right, and j by tau jt will be there, yeah, jt. So, it is Kp into A 1 minus, here it will be half cos of t by tau, right, or not half, half will be included in the definition of cos, because e to the power I theta plus e to the power minus I theta by 2 is cos theta. So, it is cos of t by tau. So, what will be my response? So, at t equal to tau, see that t equal to tau, the value will be equal to 0, and at 0 the value is also equal to 0. Okay? So, this is, let us say, Kp into A, this is y prime t and this is t. So, it will be like this. Right. So, 0, then tau, then 2 tau, 3 tau, etc. Right. So, it will continue oscillating without any damping effect, and that is why it is undamped system. The y prime is not going to decrease. So, obviously, what is the corresponding period of oscillation? Is tau, and that is the natural period of oscillation as we have discussed. And the natural frequency of oscillation will be simply 1 by tau. Okay? So, that is the natural period of oscillation. So, second order underdamped response, it has got a specific characteristics, and the response we can characterize as we have discussed by the overshoot or percentage overshoot, by decay ratio, by this period of oscillation capital T, which is 2 pi into tau divided by 1 by under root of 1 minus zeta square. Then response time and rise time, and finally we have discussed about the natural period of oscillation. So, with that, that is all about the dynamic response of a second order system. Next we will focus on the origin of the second order system. Right. Similarly, just like we have noted previously, that first order system may be a pure capacitor, or a type 2 or case 2 first order system is a capacitor plus a resistor in series. So, here we will discuss about the origin of this second order system, right. Physically, a second order system, there are 3 sources. So, physical origin of second order systems. First one is referred as multi-capacity. That is, 2 first order systems in series, right. The second is a first order system. This we will discuss later. First order system fitted with a controller. Right. As we don't know the controller, I have not introduced the controller so far. So, we will discuss this or skip this discussion regarding the point 2 of the origin of the second order system. Let us keep it pending for the time being. We will discuss it later. And the third is inherent second order system. So, we will discuss about this and this in this maybe in this and in the next session. Now, multi-capacity. Multi-capacity second order. That is, as we have noted here, that it is 2 first order in series. Now, this combination may be in 2 different ways, right. It may be non-interacting capacities and interacting capacities. Interacting capacities. Capacities means interacting two first order system and non-interacting first order system. So, what is non-interacting? See, if I connect first order system 1 and 2 in series, if the performance of 1 influence the performance of 2, but the performance of 2 is not influencing the performance of 1, it is called non-interacting. So, there is a hierarchy of influence. Performance of 1 can influence 2, but there is no reversal of this same phenomena, like 2 cannot influence the performance of 1. Whereas, for interacting capacity, this reversal happens, like 1 can influence 2, 2 can influence 1 in the gross output, and finally both they will be affecting the gross output, right. So, the example, see, we have 2 tanks fitted with linear valves and they are at different levels. The first tank is above and over the second tank. Here the dynamics is represented by H1, this is Fi, this is R1, this is R2 and this is H2, right. This is F, or let us not write this. So, this is the final output and this one is the input. Area of the tank here is A1, this tank has an area A2. Now, you see that we can easily write the system equation for tank 1 and tank 2, and also we can note that the level of the tank 1, which is the performance or the outcome, right, will dictate the flow rate here and can influence H2, but the level H2 cannot influence H1. So, this is typically the non-interacting capacity. So, we write the system equation as A dH1 dt is equal to Fi minus H1 by R1. So, in deviation variable form, this will also assume or remain same. So, if we take the Laplace considering this H1 prime bar 0 equal to 0, then A1 R1 S plus 1 whole bracket H1 prime bar is equal to Fi prime bar. So, H1 prime bar divided by Fi prime bar is equal to, and here it will be R1 divided by A1 R1 S plus 1. Now, for the second tank, we can write A2 dH2 dt or dH2 prime dt is equal to the inflow is H1 prime by R1, outflow is H2 prime by R2. So, A2 R2 upon taking Laplace S plus 1 whole bracket H2 prime is equal to R2 by R1 into H1 prime bar. So, H2 prime bar divided by H1 prime bar is R2 divided by R1 divided by A2 R2 S plus 1. Now, finally, the output is H2 and input is Fi. So, H2 prime bar divided by Fi prime bar is H2 prime bar by H1 prime bar into H1 prime bar by Fi prime bar. So, that is a product of the two individual capacities transfer function, and what we get? This is R2 divided by A1 R1 into A2 R2 S square plus A1 R1 plus A2 R2 whole bracket S plus 1, right. So, it exactly corroborates with the second order transfer function, right. So, see that this one we can call this is tau P1, right. This is basically equal to tau P1, this is Kp1 gain, this is Kp2, and this one is tau P2. So, we can write that this is equal to Kp1 into Kp2, this is tau P1, this is tau P2, and this one is tau P1, this one is again tau P2. So, in a sense, for non-interacting capacities, we will have Kp1 into Kp2, then tau P1 tau P2 S square plus tau P1 tau P2 whole bracket S plus 1. So, overall gain Kp is Kp1 into Kp2, tau the natural period of oscillation of the resulting second order system will be the under root of tau P1 into tau P2, that is geometric mean of tau P1 comma tau P2, right. And zeta, see this should be equal to 2 tau zeta, right. So, zeta is equal to tau P1 plus tau P2 divided by 2 into tau. So, it is tau P1 plus tau P2 divided by 2 by tau P1 tau P2, right. So, it is arithmetic mean by geometric mean of tau P1 and tau P2. It is quite clear. So, this is arithmetic mean by geometric mean. Now, point what we have to note here is that for two positive and distinct numbers, that is tau P1 and tau P2, arithmetic mean is always greater than geometric mean. So, zeta is greater than 1. So, this type of capacity is what we connect, right. That is in non-interacting multi-capacity, they are always an overdamped system. If tau P1 is equal to tau P2, that is two first order capacities are identical, then zeta equal to 1, that is critically damped. But in no situation it will be underdamped, that is zeta less than 1. In no situation. So, overdamped non-interacting multi-capacity can never be an underdamped system. It can never produce oscillatory response, right, and to a step input in Fi. Definitely it can produce oscillatory response if the input itself is oscillatory. That we will see in the when we go for the chapter of frequency response, right. towards the last few classes of process control, right? So that's all for this session. In the next session, we'll continue our discussion with the response and the physical origin of this interacting second order system or interacting multi-capacity second order system. Thank you.